Welcome to our new unit. We are finally going to start doing things that look like chemistry. Now, before I get started on this first lecture, I want to make sure that you understand the instructions that were given in Google Classroom, which is that there are 3 different lectures for this particular section of study. And these lectures need to be viewed in the window of opportunity that is written on Google Classroom. So each lecture should be watched either on the Monday or Tuesday or Wednesday or Thursday, Friday that's listed in Google Classroom. These topics all build on each other. So if you skip it and you come to class, you won't know what's going on. So please make sure that you watch the videos when you're supposed to watch the videos. We're trying to get everybody a little better time management as we go into this new topic and just about going into a new quarter. So this is the first of 3 lectures that is going to focus on bonding. Now, this is going to be an introduction to bonding, and then we will have more details on different types of bondings as we go through the next several weeks. So here we go. So let's start off with first the big question, which is how do we hold things together at all? Because up until this point, all we've talked about are individual atoms. We actually haven't talked about atoms coming together for any reason whatsoever. So this is going to be talking about holding atoms together. And the first thing I want to mention is that here we have intramolecular forces, and that's what mostly we're going to be talking about in this particular section. So we're talking about bonds, ionic bonds and covalent bonds. We're going to focus on covalent bonds first. But that doesn't mean that bonds, intramolecular forces, are the only thing at play here. If we were in a regular non-COVID time, if you will, we would also be talking about intramolecular forces, which chemists like to abbreviate as IMFs. These are not bonds, but forces that are between molecules. So it might be what holds one water molecule to another water molecule, right? It's these forces of attraction. And there's several different ones. There's 3 or 4 here that you can see. And this is what is responsible for making things into phases other than gas. Last unit we talked about gases and how there were no forces of attraction, but in reality that's not true. There are these IMFs, these forces, and these are what cause things like water molecules to stick together. So we don't always just have water vapor, we can also have liquid or we can have solid. Now, but because we're in this strange time, this is going to be skipped. We're just going to set this aside, and if you take AP next year, you'll certainly learn about them. But we're going to focus on the basics. So we're going to be focusing on the intramolecular forces, which are the bonds that hold atoms together that help make the different compounds and molecules. So this unit is going to touch on several things. It's going to touch on bonding. Bonding in general involves energy and the interaction of electrons with atomic nuclei. The bonds are within the compound itself. Oh, sorry about that. They're within the compound itself, so they're holding one atom to another, and it only actually involves the valence electrons. So this is something we've learned about before that's coming back. We need to be able to count the number of valence electrons that are in any particular atom. And then, like I said, it's worth mentioning that there are these important intermolecular forces, or IMFs, but we're going to skip those for this year because we are all not getting quite as much class time, as we would like. So before we jump into the details, the big question here is why would atoms bond at all, right? Why would they even go through the trouble? And the answer is complex, but at the same time, it serves a very simple purpose, which is bonding achieves stability. And that stability comes from lower energy state existences. Okay, in nature, things prefer to be in the lowest energy state possible, and that by default brings across this stability. And atoms become more stable when they have an electron configuration that is the same of that of a noble gas. So think about where noble gases are on the periodic table on the far right-hand side that we learned a month or so ago. And all noble gases have a full octet. And that's where the stability comes from, is that full octet. So think about, if you will, that video that you watched about the formation of salt. Those were two highly reactive elements when they were in their elemental form. When you have just sodium and it's not bonded to anything else, it is incredibly reactive. That's why it has to be stored in a special way and has to be handled very carefully. When you have chlorine by itself, right, it is a toxic, dangerous, poisonous gas. But when you put these two elements together and a bond forms, what you end up with is that table salt that was used to salt the popcorn. And table salt is very stable. We put it on our tables, we put it in our kitchen. It can be in your cabinet for literally decades and it doesn't go bad because reactions are not happening because it's incredibly stable. And so that's what elements are trying to achieve when they bond. There are three big types of bonds. We're going to do one at a time. The three big types are metallic bonds, ionic bonds, and covalent bonds. So metallic bonds are something that we're not going to spend a lot of time on, but they do exist, and I think that we need to talk about the fact that they exist because everybody wants to know, what about all the metals? So metallic bonds occur when you have a bunch of metal atoms and they have a bunch of electrons, and all of those electrons are together and they're like in this big electron soup all around the metal atoms or the metal nuclei, and it gives them a sea of electrons, and that is part of the reason that metals are like malleable and can conduct electricity. So they do exist, it just happens to not be something that's generally taught a lot, especially in Virginia chemistry. And then there's ionic bonding, which is the transfer of electrons between a metal and a nonmetal. And we've started learning about this in the previous unit. Metals like to give up their electrons to become positive, and nonmetals like to gain those electrons to become negative, just like in the salt example. But first, we are going to talk about this one, which is covalent bonding. Covalent bonding is the sharing of electrons between two nonmetal atoms. So for the next 2 weeks, we will be focusing on nonmetals and how they covalently bond to each other. So I just hinted at this, which is covalent bonds occur between nonmetals. So a lot of things we've learned in the past are going to come back now. So think about your periodic table. It's good to have one handy pretty much every day from this point forward. And think about where the nonmetals are. The nonmetals are this section here. So when we talk about covalent bonds, we are talking about bonds between atoms that are in this section of the periodic table. And what happens is that they're all trying to get electrons to fill out their octet, but they don't have enough electronegativity to actually take an electron from the other atom. And that might be a little confusing at first because we learned in the last unit that electronegativity increases as you go across. So how can they not have enough electronegativity? Well, it's a little more complicated than not having enough. It's really more about having more than the element you're trying to steal an electron from. And since they don't have enough to steal one away, what happens is the electrons end up having to be shared. And the electrons are always shared in the unpaired valence electrons. So unpaired, remember, is when we did orbital notations. And remember the rule was that when you got to the p orbital, remember how we had to spread them out before we paired them up? Well, that was so that we could identify the unpaired electrons because these are the ones that are going to want to bond. So, I've got some marks on my slide there that I didn't get rid of. Sorry about that. So here, the bonded atoms actually become part of each other. There's this attraction between the nuclei and the electrons, but you'll notice that this attraction is occurring between everybody, right? This is an incredibly strong bond. And in a lot of ways, it is stronger than an ionic bond. And the reason that I say that it's stronger is because this type of bond, this sharing where they actually incorporate those electrons into both atoms or all the atoms that are a part of it, they cannot be easily broken down. You can't dissolve covalent compounds in water like you can ionic ones. You can't melt these bonds away either. And these types of compounds are not going to conduct electricity because you can't pull them apart and make them charged. Instead, they're literally glued together by this incredibly strong attraction to one another. Now, back to this electronegativity thing. We said that they don't have enough electronegativity, but like I said, it really has to do with the difference. So if we know that electronegativity increases as we go across the periodic table, if I take something like potassium that's on one side and chlorine that's on the other, okay, the difference is going to be really big because it increases as you go across. So potassium is 0.8 and chlorine is 3.2. This makes for a really big difference in electronegativity, so much so that chlorine can actually pull an electron off of the potassium and take it, right? This is what results in an ionic bond. But when you're talking about all of the elements that you're going to be using coming from this corner, they all have high numbers. And you can see here the difference is not nearly as great. The difference is less than 1. So when that happens, actually when it's less than 1.7, they're not strong enough to steal from each other. So instead they end up having to share. Now, do you have to know all of the numbers for every element? No, you really don't. Some textbooks and things like that will give you that chart with all of the different numbers. And you can totally look up the numbers and follow this below 1.7 rule. But easier than that is just to know that it's the atoms that are nonmetals, right? When they bond together, it's always a covalent bond because they're too close together, so their electronegativity differences are simply not great enough to allow one to steal from the other. So if they're not stealing, they have to be sharing. And when they share, they all share in a very similar way because they're all trying to get that stability of an octet. So here's my oxygen, right? Oxygen would normally not have a full outer ring because oxygen in its 2p, right? It would have only 4 electrons in the 2p. So it really needs 2 more. Well, it's going to get them by sharing with 2 hydrogens because each hydrogen only has 1. So it turns out that each one is willing to share one of those unpaired electrons. And that happens in the same way every time. And that's really important because what that means is that water is always going to bond this way. Water's always going to be H2O, no matter where it comes from. If you get a glass of water from your sink, it's going to be 2 hydrogens bonded to an oxygen because oxygen needs 2 more electrons and each hydrogen needs 1 more. And if you take that glass of water and you dump it out into the river and it mixes with the river water, right? And then you scoop up some new river water in your glass, all of the water molecules are still going to be H2O. And as that water eventually goes all the way out to the ocean, if you were to take a sample of water from the ocean, still H2O. The compound never changes. If that ocean water is evaporated up into the clouds are water. If the clouds rain or snow back down onto the surface of the planet, still H2O. So this is a predictable way that oxygen and hydrogen behave. Right? The molecular formula tells you exactly what you have, and it's always the same. Now, how do we know that it's H2O? Why do we know that it looks like that? Well, because we're looking at the valence electron. So we're going to go through the 3 different types of covalent bonds, and we're going to practice some, so don't worry if right now it seems a little confusing. We're going to circle back around, but first you need the information so you can do it. So depending on the number of electrons that are shared between any 2 non-metal atoms, we will either have a single, double, or triple bond. A single bond comes when 2 electrons get shared, and that makes the pair. So here I have chlorine with its 7 electrons, and here I have chlorine with its 7 electrons. They both want to have 8, but they have the same electronegativity, so neither one of them can actually steal one away from the other one. So instead, the solution is they're going to share those two. They're going to basically pass them back and forth, and they're going to both take part in hanging on to those electrons that they're sharing. That's what this is right here. That is the covalent bond. And depending on how you learned how to draw these maybe in bio, sometimes we replace that dot on dot with just a single line. You can do either one, whichever one you're more comfortable with is perfectly fine. Okay, it means the same thing. So this is a single bond. It is these single unpaired electrons being shared between the two chlorines right here and creating that covalent bond. We can also have double and triple bonds. So double would be twice as many electrons, so this time it's going to be 4 electrons being shared, and that's going to give us 2 pairs. Now here, this one is kind of a mess. I'm going to show you how they got to this, but this is one pair, and this is one pair. And this is one pair, and this is one pair. And then here are, instead of the double dots, right here are the 2 lines. So I just want to show you how they got this. Okay. So if I draw this over again, I've got oxygen, which has 6 valence electrons. I have carbon, and I'm going to use X's just so you can tell them apart since it's hard to change colors on this program, like this, okay? And so now you can see that these singles and these singles, that dot and X, that's where this dot and X came from. And up here, same thing. I'm going to take this dot and X and this dot and X. Now I put these far apart so you could see, but that's where these came from. And then this is the cleaned up version. So because we are sharing 4 electrons, okay, that would be the 1, 2, 3, 4, between 2 atoms, we call that a double bond. Okay. Now the last one is a triple bond. Okay, so it's either single, double, or triple. And so triple is going to be 6 electrons making 3 pairs. So here we have nitrogen, and again it's the same electronegativity, not enough to actually pull these guys apart. So instead they have to share. So we share singles. So this one has 5 and it needs 3 more, and this one has 5 and it needs 3 more. So it's going to share. So now it feels like it has 6, and now they both feel like they have 7 because they're sharing these, and now they feel like they have 8. And again, this is the cleaned up version with the triple bond and then just moving the dots out of the way so it looks nice. So covalent compounds can be single, double, or triple bonds. There's no such thing as a quadruple bond, so please don't ever, ever, ever draw a quadruple bond. Now, how do we know? We're going to go through and show you how. This is like slowly building up our skills, and it's really simple. You already know how to do almost everything. You just have to put it together. We've reached that magical tipping point in chemistry, okay? So we look up nitrogen on the periodic table. We look at where it is, and we should all be able to easily draw the Lewis dot diagram. Then we look at what we just drew, and we see, well, how many of these are unpaired? Well, there's one, there's one, there's one. There are 3 unpaired electrons. So that tells me that nitrogen can make 3 bonds. Now, does it have to be a triple bond? No. It could be a triple bond. It could be a double and a single. It could be 3 singles. But it can't be more than 3. That's all it can do. Okay. So this is how we're going to tell how many bonds are likely to happen. So let's try another one. Here's oxygen. All right, so if we come to oxygen and we look it up on the periodic table, we should see that it has 6 valence electrons. 2 of them are unpaired. So that means that oxygen is likely to make 2 bonds. And again, it could be a double bond. It could also be 2 separate single bonds, but no more than 2. So you can see this is just using what we already know to do something new. We'll do a few more here. So this is fluorine. Fluorine, if you look on your periodic table, has 7 valence electrons. Only one of them is unpaired, so that means fluorine would like to make 1 bond. Well, if you can only make 1 bond, it must be a single bond. Okay. and then a few more here. I'm going to go through these a little bit faster because we should have the idea now. So carbon gets 4 valence electrons, all of them are unpaired, and it can make 4 bonds. And then hydrogen is one of the strange exceptions. Hydrogen, remember, only has 1 dot. It only has 1 unpaired electron, but it can only make 1 bond. And that is because, remember, hydrogen and helium are in the first energy level and they only have a 1s. So there is no 1p, so they can only hold 2 in total. All right, now sulfur. Notice where sulfur is on the periodic table. It's in the same column or group as oxygen, so it has the same 6 valence electrons, which means it has 2 unpaired, and it's likely to make 2 bonds. So there's patterns that we've already learned that we're going to tap into in order to do things in this unit. Now, the last thing that we're going to cover is drawing structures, because we're still just looking at singular atoms here. So let's talk about drawing structures for a few minutes. I'm going to show you how to do it. I'm going to show you a couple of examples, and then that will be the end of this presentation, and then you'll have some practice problems to do on your own. So here we go. Now, I'm going to show you 2 different ways to do this on each slide. If you are someone who likes to have sets of rules, you like to have like a list you can check off to know you're doing it right, well, this is what these are for. These are for you. You can follow these rules, and they're in your notes, and for these rules, they will walk you through the steps on how to construct a Lewis dot diagram for a compound. Now, not everybody needs these rules. Some people have incredible spatial awareness or spatial intelligence, but not everybody does. This is one of those things that a small percentage of the population has. If you happen to have really good spatial intelligence, you probably won't need these rules, and that's okay. And I'll show you how to do it that way as well, right? Do the way that works for you. So here are the steps if you need steps to get you started. What you will do is you will take whatever compound you are given, and the first thing you'll do is use your periodic table and count up the total number of valence electrons for each atom in the compound. Then you will put one of those atoms in the center of what's going to be your compound, and then you're going to draw a line, a bond, to all of the other atoms, connecting it to the one in the center. So you do have to have some idea about which element can make the most bonds, because that's the one you want in the center. Okay. And remember that each line you draw represents 2 electrons being shared. Okay. After you do that, you'll have electrons left over from that big total that you made. So from that big total, you'll start to distribute all of those other electrons out into the rest of the molecule. And then if needed, you can go back and put any extra leftover electrons on the central atom, but they have to be in pairs, and then you check to make sure everybody has followed the octet rule. And if anybody is short or overcrowded, you can move a few of them around to make double or triple bonds. Okay. Now I know that's a lot of random things right now until you've seen an example. So let's do an example, and I'm going to use these rules to show you. So first, using the rules. All right, so this is carbon tetrachloride, CCl4. Now, if I'm following those rules, the first step is to count the total number of valence electrons. So there's carbon, and here's chlorine. So I'm looking on my periodic table, and I see that carbon has 4 valence electrons, and I see that chlorine has 7. Okay, so 7 chlorine, but there's 4 of them, so that's 28. So now I'm going to add them up. 4 plus 28, that's a lot, right? That's 32 valence electrons I need to put in my drawing. Now it says to put somebody in the middle. Well, I'm going to put carbon in the middle because he can make a lot of bonds, but chlorine only has 1 electron left to make a bond with. So I'm going to put carbon in the middle, and then it says to put all the other ones around it and connect it with lines. So that's what I'm going to do here. Just like this. Okay, and it says, so now I'm going to start counting, right? So this was 2, 4, 6, 8 electrons that I've dealt with so far. I need 32 in my picture. It says to distribute the extra ones around in pairs. So I've already done 8 by drawing my lines. So here comes 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So now I've got all 32 electrons on my picture, and I can double check. Carbon right now has 2, 4, 6, 8 around it, which is what it wants. And chlorine has 2, 4, 6, sharing these, 8 around it, which is also what it wants. So this is all good. Everybody's got the octet, and I've accounted for all of the electrons. Now, let's say you're looking at this and you're thinking, why do I need all those steps? I can just see what happens. Well, that's great. If you can see what's going to happen, then that's awesome. But if you can't, follow the steps. So this is the other way of doing it. Instead of counting up the electrons, you're going to do something very similar, but what you'll do is you'll just put these guys out on your paper, right? So I'm not counting the electrons, but I'm just kind of sprinkling them around the carbon because I know the carbon is likely to be in the middle because it can make the most bonds. And then what I do is I share the dots that are singles. So I'm going to literally connect these two, and these two, and these two, and these two. And again, you can see that what I have is the same structure when it's all said and done. So this is more like eyeballing it, and this is more being official. But they both work. You should do the way that works for you. Okay, so let's go to the next example. All right, this one is NH3. Again, we'll do it both ways. So first, with the following the rules, right? Look on your periodic table. Nitrogen has 5. Hydrogen has 1, but you have 3 of them. So that gives you a total of 8 electrons that you have to draw. Okay, it says to put something in the middle. You never put hydrogen in the middle because hydrogen's like the corner of a puzzle piece. Once you use it, you can't do anything else with it. So there I go. Now I count my electrons. Each line represents 2, so that's 2, 4, 6. I've put 6 electrons on so far. I need 8. Well, I can't put any more on the outside electrons, so it says then I have to go to the inside. So 8 is what I'm looking for, so I've got 6 and ... there's 8. Okay, and then just to be sure, I double check. Nitrogen needs to have 8, so it's got 2, 4, 6, 8. It's good. Each hydrogen needs 2, 2, 2, 2. It's good, so that's fine. Okay, again, if you want to do the eyeball it version, that's okay too. It's very similar, just a little less structured. Again, I put my nitrogen with my Lewis dots, and then I know I need 3 hydrogens, and I happen to see 3 unpaired electrons, so I sprinkle around my hydrogens, and then I literally connect the dots. So again, both ways work, and we end up with the same picture at the end. All right, we're going to do one more. This one's a little harder. This one is CH2O. All right, so again, using the rules first. So there's my C, there's my H, and here's my O. This has 4 and 1. Oops, but I have 2 of them. And this has 6. So that's 10, 11, 12, it looks like, electrons. I have to decide what goes in the middle. Well, carbon can make 4 bonds and oxygen can only make 2. So I'm going to put carbon in the middle. Right. Now I have to attach everybody, right, with a line, it said. That was the next rule. All right, so that's done. Now it says distribute the extra electrons in pairs to fulfill the octet rule. Well, I can't give any more to these guys. This one's got 2, right? So this would be 3, 4, 5, 6, 7, 8. So this guy now has 8. These are both happy. But here's the problem. Notice that how many does carbon have? Carbon only has 2, 4, 6. That's not enough. So I need to distribute them by making a double or triple bond to fulfill the octet rule. So instead of this oxygen hogging them, what happens is this oxygen shares them. So now I have 2, 4, 6, 8, and I still have 2, 4, 6, 8. So this is an example of making a double or a triple bond, okay, which is a little tricky, but it gets easier as you go. And then I'll show you my way over here that I like to do. So again, I put all my dots on first rather than last. I still do the connect everybody once, single to single. Oops, there, make them connect. There we go, single to single. But I like this way because now I can see, oh no, this guy still has a single one, this guy still has a single one, so I'll connect those as well. But again, you see, we get exactly the same answer. So do whichever way makes you feel better. Okay. And it can be messy, that's okay. You can always do a nice clean version at the end. All right. So the last thing to touch on are polyatomic ions. And these are on the back of your periodic table if you got one at school. Right? They're groups of atoms that happen to have a little charge next to them. So if you have one of the periodic tables from school, flip it over and take a look. And you'll see these are all nonmetals, right? But they have this charge written up here. So this charge is because the number of electrons have been tinkered with. Most of them are negative, right? Which means that electrons were added, but you also have NH4 plus. This one means that you removed an electron to make it positive. So if you have to draw a polyatomic ion, it's covalently bonded nonmetals, but they have a charge. Those charges actually are going to help you because you're going to follow all the same rules, and then you're just allowed to add or subtract the number of electrons that you see indicated by the charge. So let's just do one, and then we'll call this the end of the lecture. So here I have NH4. So again, if we want to use the rules from before, that has 5. And then I have hydrogen that has 1, but there are 4 of them. So 5 plus 4, that's weird, right? That's 9. 9 electrons. How am I going to get 9 electrons in there when everything has to be in pairs? Well, this plus sign means that I get to take one off. Okay. Do I know which one I want to take off yet? Maybe not. That's okay. I can still follow the rules of spreading them around, right? And then counting them all up. So 2, 4, 6, 8. Nitrogen's good. Each hydrogen is good. So at this point, I've got 8 electrons, and I'm allowed to take one away, so I'm going to take one off anyway. So this is good, right? But this is also kind of weird. When it has a charge, you have to do this. You have to put brackets around it, and then you have to put the charge outside. That lets the person looking at it know, yeah, I did that on purpose. I took one away, okay? Because normally it would have 9, right? We saw that when we added up the numbers. So if I did mine my way, I would do nitrogen with the 5 dots. I would add in my 3 hydrogens, each one with 1 dot. Connect the dots, connect the dots, connect the dots. Oh, but now I need my 4th hydrogen, and this is where it gets weird. I don't have a single electron anymore, so I'm like, oh no! And then look at what's left. That guy right there's left, and I don't want him there, but that's okay. I get to remove an electron, so I can see by drawing them the way I draw them that the electron that I actually removed was the one that was left over on the nitrogen, so I can get rid of him. Boop, now he's gone, okay? So this is a lot of information to get you started, all right? This is about a normal lecture. It's been about 30 minutes. And what we're going to do now is practice. It's very important to practice these. It's also very important that you turn these in on time. So for the first lesson, we've just had lecture 1. The first lesson that goes with this, where you're going to practice, it is due on Wednesday, guys. If you turn it in on Wednesday, you will get feedback, and that will allow you to redo problems that you get wrong, right? And turn it back in. Get a better grade, right? If you turn this in past Wednesday, you get no second chance. You don't get that opportunity to turn it back in, right? If you turn it in past a week from Wednesday, right? If it's 1 week late, you don't get to turn it in at all. Everything has a 1 week wiggle room, but if it's not turned in on time, you don't get feedback, okay? So please know, if you are late, it's one and done, right? No feedback, no do-overs. So please, let's get everybody moving in the right direction, right? If it's late, no feedbacks, no do-overs. If it is more than 1 week late, I'm not taking it. It's a 0 because everything builds on itself. And to go back and do it later is just chasing points but not learning. And I don't have time for that, and neither do you. So now make sure that you do your practice exercises with your notes in front of you, and you turn them in so that you can get feedback and make corrections or ask additional questions if you need to.